Welcome back. Lesson 15 Applications of Congruences. Congruences have many applications to discrete mathematics, computer science, and many other disciplines. We present a few here. First application is that of hashing functions. Suppose a company maintains records for each of its customers. How can memory locations be assigned so that the customer records can be retrieved quickly? This is where a suitably chosen hashing function is used. Records are identified using a key. Notice, hashing function has to be quickly evaluated and must be onto. For instance, HK, that's your hashing function, for a key k could be k mod m. For some fixed m, typically m is the number of available memory locations. So you see, you have a computer, it doesn't have infinite space. You have an available memory, number of available memory locations. So you go modulo that m. Find the memory locations assigned by this hashing function for m equals 101. When k is this large number or when k is this other large number. Well, what are we looking for? This large number modulo 101. I have a little bit of calculation. All I have to do is divide by 101. When I take this number divided by 101, I get quotient this and a remainder this. Modulo 101, what does it mean to say modulo 101? You're aiming for the remainder, so remainder is 43. Likewise, for the other k, all I do is take that number, divide by 101. I get a quotient and I get a remainder. Now that is my memory location where HK, the information for key k, will be stored. Alright. Now, because a hashing function is not one-to-one, what does that mean? Well, because I'm going modulo 101, it is quite possible that I come up with two numbers whose remainder is the same. That is, two different keys land me in the same memory location. Aha. Now that's not okay because that's what is a collision. I already have a file in one location. I'm going to put one more file. So that is a collision. We want to avoid collisions. So we want to resolve a collision. What do you do then? You assign the first free location following the occupied. So you see, now here I have two keys. One gave me location 43, the other gave me location 28. Okay. Suppose I come up with another number. So I have occupied only these two locations. What does it say? The first free location following the occupied memory location. Okay. So suppose I have yet another number which takes me to the same location as 43. Well, right now 43 and 28 are occupied. The first location after 43 that's available is 44. I will take in there. If I come up with a key which takes me to 28, then I'll go to 29 because 28 is occupied. Okay, so you first calculate where you land, and if it's occupied, you go to the next available location. Okay, first free location, not just the very next, but the free location after it. So in other words, you may use a linear probing function called HKI. You're looking at HK first and then I modulo M to look for the first free memory location from here to m minus 1. So if say 29 were also occupied, you will look at 30, then you would look at 31 and so on. You look for the first free location until modulo 101, that is until 100. Okay, so a hashing function usually comes with its own probing function. Here is another pseudo-random numbers. Here are another application of congruence. Random numbers are often needed for computer simulations. Okay, these are two words. Computer simulations require random numbers. Numbers generated by systematic methods are not truly random because they are systematic in some sense. They are therefore called pseudo-random numbers. The most commonly used procedure for generating pseudo-random numbers is what is called linear congruential method. Linear and congruential. What does that mean? Well, start with 4 integers. One is modulus, the other is multiplier, the next is increment, and the last is seed. Modulus, multiplier, increment, seed. Okay. Now, the multiplier A has to be between 2 and less than m. Okay. From 2 until m minus 1. What about the increment C? C has to be between 0 and m minus 1. And your seed x naught also has to be between 0 and m minus 1. So what do? You start with a seed x naught. You generate a sequence of pseudo-random numbers. That's a sequence xn. What does that mean? x1, x2, x3, so on. That's a sequence where each xn is between 0 and m for all n by recursion using a recursively defined function. What do? You start with your seed, that's your starter number, multiply it to the multiplier a, you get some number, add your increment c, you get yet another number, go modulo m, that's your first number. Okay, use that first number here, find second number, use that second number here, find the third number, and that's how you find x1, x2, x3. So that's why you start with some x0, that's called seed, and the seed is not written here. You start with x1 onwards, okay? Some computer programs need random numbers between 0 and 1. You want between 0 and 1. So notice this is going to give you integer. So what do? Between 0 and 1? Well, every random number here, pseudo-random number you generate here is less than m. So divide by m. Then that becomes a fraction smaller than 1. And because each xn is greater equals 0, each one of these number is between 0 and 1. So now you can use any modulus, any a, any c, and generate your own functions. Okay, generate your own pseudo numbers. You can try it yourself. When the c, that is the increment, is 0, then the pseudo-random number generator is called pure multiplicative generator. See, if c is 0, all you're doing is multiplying, nothing more. So it's called pure multiplicative generator. For example, the modulus 2 to the 31 minus 1 and multiplier 7 to the 5th is widely used. It can be shown that 2 to the 31 minus 2 numbers are generated before repetition begins. Now that's a hard proof. Okay. So multiplier of 7 to the 5th, that's a big number. While pseudo-random numbers generated by linear congruential generators have long been used, it has been shown that sequences of pseudo-random numbers generated in this way do not share some important statistical properties. Okay, in other words, they are not random enough. So it is not advisable to use them for large simulations. Therefore, in such cases, other methods are used to produce pseudo-random numbers. Alright, this completes lesson 15. Next video will start on lesson 16. Until then, bye.